All right. So before we get going, I'm going to re-upload the Excel part of the Excel assignment. If you've already started it, that's fine. But I had it reading as 2 kids in the Word document, and for some reason, the labels in the Excel put 3. So they didn't match up. So if you started it and you used either one, I'll kind of grade it accordingly. It would still, all the kind of answers would you would approach them all in a similar way. If you started using 3 and you've already started the assignment, that's fine. I'm just going to re-upload that file so that both of them match up and just say 2 kids. Okay. I think that's the only thing I have to mention up the top. The other thing I want to mention, I will kind of put an online quiz up as soon as I'm back to my office after class. That'll be due before we start class Monday. So it's kind of related to what we're going to cover today, and just gives me an idea about kind of how people are kind of grasping the material, and gives me an idea about kind of the exam review, how to kind of direct that a little bit, and kind of what problems I want to make sure I cover that. I'll also this weekend start putting up some YouTube videos that correspond to different questions in those practice exams, so you can kind of see me working through those problems if you're having any issues with any of them, because we definitely won't get through all of them in class. So I just a little bit on Wednesday. So you'll have those up there as well as we kind of approach that exam, which is a week from today in class. Okay. Any other questions from you before we kind of dive into things here today? Okay. So we left off last class. I had shown you this binomial distribution probability mass function. So what this did was it told me the probability of seeing a different number of successes out of a certain number of trials. Okay. So the first example we'll kind of think about is, let's say I'm flipping a coin 10 times. Right. So we have a biased coin. So the probability it comes up heads instead of 0.5 is only going to be 0.4 on any one coin flip. I then might be interested, okay, well, what's the probability I see 4 of these 10 coin flips come up heads? Okay. So I've got 10 trials, that's my N. My probability of success on any one trial is 0.4. And the probability I'm interested in finding the number of successes I'm interested in finding the probability of would be 4. So X would be 4 here. From there, I've got that binomial formula in front of me. It's just a matter of plugging those 3 things in. Everywhere I see an N, I'll put 10. Everywhere I see X, I'll put 4. Everywhere I see P, I'll put 0.4. And from here, it's just a matter of getting used to entering these into our calculator. So I mentioned kind of finding that factorial on your button on your calculator. If you haven't found it yet, I highly suggest looking for it on the calculator you plan on using on Friday. If you can't find it, let me know, or Google it. You'll probably be able to figure it out that way as well. But even if we didn't have that factorial button, you can kind of imagine here, right? I can simplify some of this math. Instead of trying to enter this onto my calculator, do the math you can do in your head ahead of time. 10 minus 4, hopefully we can do is just 6. Get rid of a bunch of parentheses there and don't have to worry about making a mistake there. 1 minus 0.4 is 0.6. Kind of write that in. 10 minus 4, 6. So if I were to write out, right, one thing might be to do is in my calculator, put 0.4 to the 4th times 0.6 to the 6th. Whatever that is, write that number down. Now figure out what this other component is. Once I have this number, multiply it by the other one, and I'll be done. I can kind of break this down into parts. Right? So breaking it down into this fraction over here, if I write out what that is, remember the factorial is just start with that number and multiply down to 1. 4 times 3 times 2 times 1. 10 minus 4 we said was 6. So 6 factorial, 6 times 5 times 4 times 3 times 2 times 1. Now we'll notice if I write this out, like I could type all this in my calculator. I don't even need the factorials. But also if I look at this, everything here cancels. And now I'm just left with 10 times 9 times 8 times 7 divided by 4 times 3 times 2 times 1. Right? So a lot of stuff will simplify. It gets a lot easier. But if I try to enter this all in my calculator one time, it's easy to make a mistake. Just place a parenthesis. And so breaking it down into parts, doing the math that we can do in our heads ahead of time, I think that makes it so we're less likely to make an error. Okay. Any questions there before we keep moving? If I actually enter this in my calculator, up 0.25. Someone have a question? Okay with this for right now? We'll go through more examples here. I think just seeing more will help. So one thing we can start to think about, right, before I go into this next example, I'm going to kind of cheat and go, work ahead a little bit. But let's say I flip a regular coin 100 times. Actually, make it easier. 10 times, right? And it's a regular coin, so the probability to see a head come up is 0.5, right? What would you think would the most likely outcome be out of 10 coin flips for the number of heads that I see from a regular coin? The most likely outcome would be to see how many of the 10 come up heads? 5, right? So what if I've got something like, 100, right? If I flip a coin 100 times, what's the most likely number of heads that come up? 50. So what are you doing in your head there, right? Like you intuitively kind of know what the most likely or what the expected value should be. Well, another word for the expected value was just the mean of this random variable x, right? So the way that we're going to find the mean is actually just n times p, right? That's what you were doing in your head. 10 times 0.5 gives you 5. 10 times or 100 times 0.5 gives you that 50. Right? So this actually applies no matter what the probability or number of successes are. So n times p will tell us our expected value or our mean, and that should be the number of successes that is the most likely. You can kind of imagine if I were to graph this out, seeing 5 heads, I'm putting that probability on the y-axis, that should be the most likely outcome. As I move further up, right, seeing 6 of the 10 is still pretty likely, but not as likely as seeing 5. And then seeing 7 of the 10, a little bit less likely. 8 out of 10, a little bit less likely. 9 out of 10. Now we start to get things that have pretty low probabilities, right? The probability that all 10 coin flips come up heads is probably really, really low. Right? So this idea works in the other direction as well. And it's that as I move away from that expected value, the probability of number of successes that are further from that expected value or the mean, those probabilities start to decline. Okay. So we can use this idea, use this fact to help us like rule certain answers out, think about around what our probability should be, and it'll apply to every single binomial example we look at. Okay. Excuse me. So let's think about this next example. Let's say I've got 5 people, right? And I know the probability that any one person has a college degree is about 0.3. What's the probability that 3 of these 5 people have a college degree? Okay. So what's the expected number of people out of 5 that would have a college degree here? The math's a little bit harder, but let's say it was 10 people. If it was 10 people, 3. So 5 people would be 1.5. So this is kind of a weird one, right? Where we've got this mean of 1.5. Right? Well, this is a discrete random variable. So what's the most likely outcome? We can't see 1.5, but we can see 1 and 2, right? So if you ever end up with a mean that has like a decimal, the most likely outcomes will now be the 2 values on either side, right? And then as we move further from that mean of 1.5, the probability of outcomes further from that point will just start to decline. Okay? So we know that 1 and 2 will be the most likely outcomes. So they should have relatively high probabilities. Now, when I say relatively high, think about it. If I were to take the probability that x is equal to 0 plus probably x is equal to 1, if I added up all these probabilities, what should they add up to? So be careful, right? So if we think about what we're doing there, we'd be taking every probability from every possible outcome. So if we add up the probabilities of every possible outcome, last class I said this is similar to the idea of adding up all the relative frequencies. So those should always add up to 1. Right? If we add up the probabilities of every possible outcome, those should add up to 1. So relatively high probabilities, well, 1 and 2 are going to be the most likely, right? There's an entire probability space of 1. So high probabilities here are going to be like 0.2, 0.3, maybe that's as high as we'll see. And then kind of declining from there. So I don't know if I'm guessing, 3 isn't very far from that mean. So I don't know. It's probably not going to have a real small probability, but it's not going to be the, as high as 0.2 or 0.3. Those would be kind of the most likely outcomes. Okay. From there, we just actually have to plug our values in. So our N is 5, probability of success on any one trial is 0.3. The number of successes we want to find the probability of X is exactly equal to 3. So those are our 3 things. Now it's just a matter of plugging them into that binomial formula. So really just getting practice kind of using that formula. So the Connect assignment, kind of the online quiz today will give you a couple problems where you actually have to sit down and work through these and give you some experience with that. But it's really not too bad if you break it down into parts, right? So 0.3 times, or 0.3 to the third times what? 0.7 to the second. Write that number down, and you can figure out what that fraction is, multiply whatever 2 numbers you end up with, and you should get 0.13. Okay. And these factorials become easier to deal with. You don't even need the factorial button. Like 5 factorial, it's a little bit easier to write out and think about. So kind of giving you these smaller values, it becomes a little bit easier to do by hand. Okay. Any questions here over the process or anything we're doing? Okay. So what if I asked you for the probability that exactly 4 people have a college degree? So we just found the probability that 3 people have a degree is 0.13. So which of these answers, right, even without using the formula, can you say is going to be the probability that exactly 4 people have a degree? If I told you one of these is right, which one has to be right, given what work we had just done? Yeah, so why do you know it's A? Because it's farther from the mean, so it has to be less. Yeah, right. So we had this example where, the mean was 1.5. As I move further from that, the probability should be declining. I just found the probability of 3 is 0.13. So the probability of 4 has to be something lower than that. The only value up there that was lower than 0.13 was that 0.028. Now I can recreate that by basically doing the same thing that I just did, but now X is equal to 4. Now when I plug things in, I kind of get 0.028. And you'll notice when I start getting numbers of successes close to my total number of trials, a lot of things will kind of become easier or simplify. So for instance, 5 minus 4 is just 1. Anything to the 1 power is just itself, so I don't have to do much with that. 5 factorial over 4 factorial, well, everything there would cancel except for 5. 5 minus 4 is 1, so 1 factorial is just 1. So you can kind of notice a lot of things will start canceling once you start looking for the probabilities of the number of successes being very close to the total number of trials. I'll show you an example later and kind of explain a little bit more about if we have all of them being successes, you can kind of see a lot of things will cancel. Okay. So I get that probability that X is equal to 4. Right? I then could be interested in something like, what's the probability at least 3 of the 5 have a college degree? So if I think about what I'm looking for there, the probability that at least 3 would be that the number of successes is 3 or higher, so greater than or equal to 3. Okay. So there's 2 ways I can approach this. I'll show you the first way, which makes sense in this example. The second way doesn't make as much sense in this example, but in other ones, it would make life a lot easier. So one thing we could do is think about this way. We said that the union of 2 events will just be the probability of each event added together, but then we'll subtract the intersection, right? What we double counted. Well, here, X being greater than or equal to 3, kind of really what I'm saying is X equal to 5, or is X equal to 4, or X could be equal to 3, right? We're just wanting to know the probability that X is greater than or equal to 3. So one of these number of successes. Well, once I actually ask these people, I either have exactly 3 have a degree, or exactly 4 have a degree, or exactly 5. So all of these things we would say are mutually exclusive. I'm going to only see one of them. I can't have exactly 3 and exactly 4 people have a college degree. So if they're mutually exclusive, my intersection is just 0. So to find the probability that X is 5 or 4 or 3, it's just going to be adding up the probabilities of each one of those, right? So I'll look at all the values that fit in this range. So the probability x is equal to 3, plus the probability x is equal to 4, plus the probability x is equal to 5. Well, I already found these two things, right? So really, I would only have one last probability find, use that binomial function one more time, find the probability x is equal to 5, and then add them all together. Okay. Does that make sense? Any questions? And we're really like using this idea of being mutually exclusive and then the union of events here. Okay. Any questions on that before I keep moving? So that's probably what makes the most sense here, since I've already found these two probabilities. Another way we can think about doing this is anytime I want to find the probability of an event, so call this event A, I know that's the same thing as 1 minus the complement of that event. So if the event A is being greater than or equal to 3, what would the complement be? So the complement is just everything, that's the opposite or that's not an A. So if A is being greater than or equal to 3, A complement would just be X being, less than 3, right? Right? The event and its complement should like cover every single possible value. So greater than or equal to 3 if that's event A, less than 3 would be its complement. Okay. Well, now I can think about what outcomes will be in this complement. What's the very first X value that would be less than 3? Or the lowest, what's the first number of successes that would be less than 3? Yeah, right? It's discrete. So the very first number of successes that would fit that criteria is that X could be equal to 2. Plus, what's the next possible? X could be 1. And then, one more, X is equal to 0. So don't forget the 0. 0 is always going to be our lowest possible number of successes. Well, this didn't really save me a lot of time because I'm still going to have to use that binomial formula 3 different times. But you can imagine, what if I had an example where it was like, what's the probability X is out of 100 coin flips, what's the probability I see 99 or fewer? Well, there, I wouldn't want to do the probability X is equal to 99 plus 98, but 1 minus the probability X is greater than 99. Well, there's only one thing that fits that criteria. X could be 100. I only have to use that formula one time, or the binomial formula one time. Here, it didn't really save me any time, but at least can kind of introduce the idea that we could use the 1 minus its complement in certain situations. So, we could do 1 minus the complement, or we could just find those 3 probabilities that, fell within that range that fit our criteria of being greater than or equal to 3, and then add them all together. Okay. So different ways of approaching the same problem. Okay. Any questions on that before we keep moving? Where am I at? Okay. All right. So I think I've got some, so I've got the mean. We've already talked about that, right? N times P. What ends up being true is the variance also follows a nice formula. It's just not intuitive, right? For whatever reason, the mean is intuitive for a binomial. The variance just isn't, right? There's nothing we can really connect to, but it'll be N times P times 1 minus P, right? And then if I want the standard deviation, just like always, that's just going to be one more step, which is, hopefully we all should be saying this in unison at this point, we just take the square root, right? To go from the variance to standard deviation, you just take that square root, okay? Now, where this comes from, you don't have to like replicate this or anything, but kind of the idea would be like, we're taking every possible outcome minus the mean, squaring it, times the probability we saw, X be that value, add to that, the next outcome minus the mean squared times the probability X is equal to that number of successes, et cetera, et cetera. What ends up happening if we were to write all this out, every time we have a probability, this would be the binomial formula. We would just be plugging in, 0 in for X. What you can Google the mathematical proof, but this ends up always simplifying down to N times P times 1 minus P. It's a lengthy, there's quite a few steps, but you can look it up and go through the steps and figure out this would actually always simplify down to N times P times 1 minus P. Right. So we won't ever have to prove it, but we can use this, right? We don't have to use this formula. So I'll go to a question and I'm going to come back to that. So for instance, if we use the same data, right, we've got 5 people, probably success is 0.3. What's the mean and the variance? We've already discussed how we get the mean, right? 5 times 0.3 is 1.5. And then from there, the variance is just n times p. So 5 times 0.3 times 1 minus p. So times 1 minus 0.3, right? Or 0.7, right? 1 minus 0.3 is 0.7. So these should be pretty easy questions. Like if you see one on that online quiz today or on the exam, the variance and the mean of a binomial, we can just follow those two pretty simple formulas, and you should always be able to get the mean and the variance of these binomial distributions or binomial variables. Okay. So the thing I skipped, I want to try to give a little more insight into what's going on with the distributions of a binomial variable. So notice when I have a probability of 0.5, right? So what would my mean be here? 5 times 0.5 or 2.5. So if the mean is 2.5 or the expected value is 2.5, the most likely outcomes would be 2 and 3, right? Those are going to be our most likely outcomes. Notice here, relatively high probability of occurring, 0.3. We don't get a whole lot higher than that. And then as I move in either direction from that value of 2.5, the probability of higher or lower number of successes starts to fall. Okay? So whenever I have this probability of 0.5, I end up with like a nice symmetric distribution. Right? However, when the probability gets lower, so same number of trials, but the probability of success is 0.1, notice I get the majority of my outcomes are going to be that are happening are going to be on the left side. And I get this long right tail. Right? So that low probability of success gives me a right skewed distribution. Now notice here, the mean would be 5 times 0.1 or 0.5. So 0 and 1 are my most likely outcomes. But notice here, 0 is quite a bit more likely than 1, right? So even though like 0.5 is exactly in the middle of them, the reason why it's not that they're both equally as likely is because we think about a general discrete random variable, how would we find the mean? We would take each outcome, multiply it by its probability of occurring. So 0 times 0.6 plus 1 times 0.3 plus 2 times about 0.1. So notice like that 0.6, that means that that 0 value is weighted a lot heavier. So it's influencing the mean a lot more. So even though 0.5 is exactly in the middle of 0 and 1, right, they're not going to be equally as likely because these values, even though they have really low probabilities of occurring, they're still influencing the mean a little bit, right? And so they're still pulling it up a little bit further away from 0. So that's why we end up with that mean of 0.5. Okay. And the exact opposite thing's true when we have a high probability. So here the mean would be 5 times 0.9 or 4.5. So 4 and 5 are going to be the most likely outcomes. And we end up with kind of this left skewed distribution, long left tail. What else do I want to say? Oh, so one of the reasons why we end up with this kind of unique, like not everything is symmetric with a binomial, and really the shape of the distribution depends on the probability of success, is because we're always going to be censored on either side. So when I start to get very low probabilities, I'm always going to be like censored on the left by the number of successes being 0. I can't see anything lower than that. So my probability starts to get small. It's like, yeah, I start to see 0 happen a lot, right? If I could go negative, it would kind of be this nice like down falling left tail, but it stops, right? It has to stop at 0. And then same thing when I have a high probability, right? I have to be censored or I'm stopped on the right-hand side by whatever the maximum number of trials I have is, right? And so that's why we don't always end up with kind of this nice like hill-shaped distribution, because on the left and the right, we're always going to have kind of limits. Okay? You can kind of see then, even if I kept that probability of success at 0.5, but I went to a higher number of trials, it's still symmetric. It just ends up being a little bit more granular, right? I've got a few more kind of numbers of successes I can actually see. Here, that mean 50 times 0.5 would be 25, and then it falls off as I move in either direction. Okay? So I stole this, but I always like this graphic because I think you can quickly kind of see how that shape of the binomial distribution is really just influenced by that probability of success. And you're either pulling it one way or the other. Any questions before we keep moving here? Okay. So we've went through that. I think, yeah, I don't want to waste too much time on this. But we can just talk through these and think about situations where the binomial applies. So this first one, calculate the expected number of coin flips that come up heads and 123 flips. Well, this looks like a lot of other examples we've had. We got a number of trials, 123. I want to find the mean or the expected number of times that it comes up heads. Well, we can definitely do this, right? Success, failure, I either see heads or I don't. Trials are independent. This is a perfect situation for the binomial. What about calculating the probability at least 5 out of 20 patients get nauseous from antibiotic? Well, if I have the underlying probability that when someone takes this drug, they get sick or they get nauseous, right? My probability of success there would be the same across people. I've got 20 total people, and I want to find the probability that I see at least 5. So probability of 5 plus the probability of 6 plus 7 all the way up to 20. So that's a situation. Someone either gets sick or they don't. Success, failure. Every person is independent. Whether or not they get sick is independent from the other person getting sick. So this is a nice binomial distribution example as well. We're looking for the one that's not. The third one, calculate the probability an air traffic controller makes 3 errors per week. So if we know the probability that they make an error on any one flight, that's kind of our success. They either make an error or they don't. It's kind of weird there. The error is our success, but really you think of just 1, 0, right? And so 3 errors out of what, right? The number of successes we want is 3. But what's my number of trials? How do I turn a week into trials? Well, maybe I could go and see how many flights land there in a week, but it might be variable. And so anytime I only have like a time interval, that's going to be a situation where we cannot use the binomial. I have to have a maximum number of successes or like a number of trials there. If I don't, and I have like some time interval or space interval, that's going to be the last thing that we'll talk about prior to the exam for new material on Monday, which is the Poisson distribution. Okay. So we'll go over some examples of that on Monday. But anytime I have a time interval and I'm thinking about the number of successes, that's not my binomial, that's my Poisson. I have to have like a cap, right? On total number of successes I could see. For instance, here I've got 5 customers. What's the probability 3 make a purchase? Well, if I know the underlying probability that once someone enters my store to make a purchase, I've got my probability of success. X would be 3 and N would be 5. The maximum number of people I could see make a purchase would be 5. I can put a cap on it, okay? So these are just some of the sort of scenarios we can think about for the binomial, and then kind of introducing this idea of if I'm looking at a time interval, this is really going to be the Poisson discrete random variable distribution that we'll look at Monday. Okay. All right, so I want to show you a few things in Excel, and then I have one more example I'll show you at the end that tries to connect some things we've talked about in the past to some of this stuff today about the binomial. So I'm just going to set up the 3 things that I need for my binomial distribution. Okay. So the first thing, let's say, I think the example I have in the slides is, if I go back a year or two, the number of homes that were foreclosed, if I just selected a home at random in Detroit, about 4.7% of the homes were foreclosed upon. So that probability of 0.047. Let's say I randomly select 100 homes, right? And I might then be interested, okay, what's the probability I see exactly 8 of these homes foreclosed? Okay. So I'm going to show you 2 ways you could do this. I'm going to do this a little bit different than I did the other sections. I'll show you the first way, which would be kind of a pain. So don't worry about writing this down because you won't be expected to know how to do this, but I want to do it to prove a point. So I could just use Excel to be my calculator, right? And type in that binomial distribution function. So the first thing would be 100 factorial or n factorial. So, it would be nice if I don't think you can, let me make sure. Yeah, I was going to say, I don't think that it works that way. It'd be nice if I could just type 100 factorial in Excel like this. But the problem is that there's actually, a built-in formula that does the factorial for you, which is just fact, and then whatever number you want to take the factorial of. So I'm going to take 100 factorial times what? X factorial, so 8 times the factorial of n minus x, so 100 minus 8. Let me make sure I got my parentheses right here. And that's not times. What should this be? Sorry, divided by. Right. So I would then take that, multiply it by the probability of success, 0.047, to the x power, times 1 minus the probability of success, so 1 minus 0.047, raised to the n minus x, or 100 minus 8 power. So I could write this all in, use Excel to be my calculator, and I get the probability that the number of homes foreclosed out of 100 is equal to 8. That probability is 0.05, approximately. So, I can do that, but I can also save myself a lot of time and use this built-in binom.dist function. So this basically does all the work behind the scenes for you, spits out at you the probability of whatever number of successes you're interested in. So the first thing you tell it are the number of successes you're interested in. I've got those up here, so I'm just going to click on it, comma, the number of trials, that's up here, comma, the underlying probability of success. So those are the three components that we needed and that Excel needs to put into that binomial function and then spit back out at you the answer. The only thing else that Excel has is that this binom.dist, you have to specify whether or not it's cumulative or not. Well, up to this point, we've really just been looking at the probability that we see a certain number of successes. So we would put a 0 in there because it's not cumulative, right? Cumulative would mean it would find the probability of seeing 8 plus the probability of 7 plus the probability of 6 all the way down to 0. Right? We don't want it to be cumulative, so we put a 0 in for that fourth thing. Okay. So if I hit enter there, notice I get the exact same thing as if I type that out, that entire formula out, it just saves me a lot of time. Okay. Any questions? I mean, we'll see one of those cells again, or okay. Now, just as we're thinking through here, what would the mean? If I have 100 homes, on average, how many homes would I see foreclosed here? Yeah, right. I just take that 100 homes, multiply it by the probability of success. So I get about 4.7. So the most likely outcome should be 4 and 5. Now, 8 isn't really far away from there, but its probability is starting to get somewhat small. Right? But if I'm thinking about, let's say I want to find the probability that X is less than or equal to 8. Well, if I know that the most likely outcomes are around that mean of 4.7, so 4 and 5 are the most likely outcomes. Next most likely would be 3 and 6. Next most likely would be 2 and 7. Next most likely would be 8 and 1. And we've got 0 down here. The probability that X is less than or equal to 8 would be adding up all these probabilities, which includes my most likely outcomes, my second most likely, my third, my fourth. So this is going to include a lot of the most likely outcomes. So if I add them all up, I should get a probability relatively close to 1. If the average is 4.7, what's the probability to see 8 or fewer homes? Well, it should be pretty high, right? So how do we do this in Excel, right? So I use that binom.dist function. I'm going to still tell it what my cutoff number of successes are, which is 8, right? Less than or equal to 8, comma, the number of trials is 100, comma, the probability of success, 0.047. But now I'm going to put a 1 there for cumulative. So that tells Excel, okay, start at 8, use the binomial distribution, find the probability of 8, add to that the probability of 7, all the way down to the probability that X is equal to 0. And sure enough, it ends up being a pretty high probability. Okay. Any questions there? So the only difference there is I made it cumulative, so it found the probability of 8 and anything below it. Okay. What if I wanted to find the probability X is greater than 8? Well, this is kind of like the idea we were talking about earlier with complements. If X is less than or equal to 8 is event A, its complement would be that X is greater than 8. Well, I know that the probability of an event and its complement should add up to 1. So how could I find the probability that X is greater than 8 here? Probability that it's less than or equal to 8 is about 0.95. What should the probability that it's greater than 8 be about? Yeah, those should add up to 1, so about 0.05, right? Or not 1 equals 1 minus that. How do I find the probability of an event? It's 1 minus its complement. And these two events are complements. Okay. Questions on that? Yeah. So all I did there, just 1 minus, where I had the probability that X is less than or equal to 8. I could have done this all in one cell. So I could have done something like this, where I did number of successes, comma, number of trials, comma, probability of success, comma 1. So this finds the probability X is less than or equal to 8, subtracts it from 1. So I know, 1 minus the probability of an event should be the probability of its complement. So I can do it all in one cell if I want to, or I can break it down so I can see the steps, just makes it a little bit more clear. I can kind of see a little bit more what I'm doing. Okay. Any other questions up to this point? Oh yeah, yep. So the ordering always goes number of successes X, number of trials N, N, probability success P, and then the last thing is 1 if you want it to be cumulative, 0 if you just want the probability of exactly that number of successes. Any other questions before we keep moving here? Okay, so one thing that's kind of interesting, and at least makes, hopefully shows you that I'm not full of it. Let's say I take like all these values for X, and I want to find, a bunch of different probabilities. So the probability I see 0 successes or 0 homes foreclosed, 1 home foreclosed, 2 homes foreclosed, etc. So I'm going to try to find the probability X is equal to these different values over here. So I'm going to do the first one, binom.dist. I want the probability of 0 successes, comma, out of 100 trials, comma, and the probability of success is 0.047. And I want the probability of exactly 0 successes, so not cumulative. I want to put a 0 in there. So I hit enter. Well, I want to copy this down, but if I do that, I have a problem. All right, I just want that X value to update. The number of trials and the probability of success, those aren't changing at all. So I'm going to Command T or F4 after selecting those and freeze those cell references. Okay. Now, once I do this and I copy this down, notice it lines up with what I would think. If the mean is 4.7, 4 and 5 here are the most likely outcomes or have the highest probability of occurring. And then as I move further from that value of 4.7, the probabilities decline. If I look at the left side, here as I move further from 4.7, the probabilities are declining on the right side of that distribution as well. Yep, I'm moving fast. Yeah. I'll post a complete version of what I've worked through in class here as well. So you're going to have that to look at. And you, in practice, like this is probably more so something that you would want to do. Because let's say like I'm thinking about home foreclosures here, right? If I'm an insurance company or something, I want to know like what's the probability of my X number of homes that I've got. What's the probability that one of them forecloses next one? 2, 3, 4, right? And if those probabilities start to get high of like 20 homes out of then I'd be really concerned as that company, right? So this is something setting this up to look at the different number of successes is something that is pretty practical. Okay. Because you're likely not going to just be interested in one number of successes. You likely want to know the probability of a wide range, right? Any other questions? We keep moving here. So the one reason I also set this up is then you can also prove to yourself, well, look, is this binom.dist cumulative function actually working correctly? So if I use that sum function and I add up the probabilities from 8 and below, hopefully I get the exact same thing as when I was using that binomial distribution function, but making it cumulative. Sure enough, I do, right? So this stuff's all kind of checking out, right? Any other questions about Excel? Got one more kind of by hand example I want to show you. I think that gets through everything that I wanted to show you here. Yeah, because we built this out. Okay with this? Okay. So let's think about maybe instead of the number of homes foreclosed, I flipped the example because I want to have a high probability. So that's why I'm doing this. So I'm still looking at 100 homes, but let's say, let's say the probability of success is about 0.95. So now I'm thinking about a success would be that the home is not foreclosed, just so I can get a high probability for this specific example. So it makes a little more sense. What if I then say, okay, what's the probability that I see less than or equal to 99 of the homes not being foreclosed? Right? So the reason why I'm setting it up this way is because I want to make a couple points. So the first one is, this is going to be insane if I try to think about everything that fits this criteria, add up all those probabilities. I'm going to be using the binomial function, 99 plus when it's 0, so 100 different times. That's going to take forever. I would never ask something like that in the exam. Doing it by hand, it doesn't make any sense. But I know that the probability of an event is also equal to 1 minus its complement. So what would the complement be here? Yeah, you're kind of jumping the gun, right? You're seeing the, thinking ahead. It's really that x is greater than 99, right? That would be the complement. But because it's discrete, what's the only outcome that fits this criteria? That's when x is equal to 100. Yep. And now I only have to use this function one time, right? So now I do n factorial, so 100 factorial over x factorial times n minus x factorial, because n and x are the same thing now, right? X is 100, n is 100. Probability of success to the x power, so times 1 minus the probability of success to the n minus x power. Well, notice when I want the number to know the probability of the number of successes, and it's exactly equal to my number of trials, so every trial is a success. 100 minus 100 is 0. Anything to the 0 power, this will always be 1 when you're trying to find the probability that all trials are successful. Notice here, 100 factorial of 100 factorial cancels. 0 factorial is 1. So when you're looking for all trials to be successes, this fraction is always going to be 1. So really all I'm left with when I want to find the probability that all trials are successes is the probability of success raised to whatever power, whatever number of trials I have. And obviously here I was going to use that and 1 minus to find the probability of what I eventually wanted. But right, I just want to show you kind of how a lot of things cancel when you're trying to find the probability that all trials are successes. And we can relate this to something I talked about in the past. So that video I put up when we had the snow day, I think at the end of it talked about this old casino where they had a roulette table and it came up black 26 times in a row, right? So I can relate this to the binomial. So with a binomial, we have independent events, right? So the idea was if I wanted the intersection of two events, if they're independent, I could just take the probability of each event and multiply it by each other. Right? So here, when I say, well, what's the probability that all these trials are successes? So if I think about like the roulette table example, what's the probability that it hits black on the first spin and hits black on the second, all the way to the 26th, right? If I spin this 26 times. Well, that's the same as saying the probability that I get black on the first spin. Because they're independent events, I can just multiply these probabilities so that I get black on the second spin, black on the third, etc. So if I have one probability, like when I spin that roulette table, the probability is always 0.5 or just shy of 0.5, right? Because it's got like a one green square or something like that. I'm not really big into like casino gambling, but I believe that's how it works. So I've got one probability and I'm going to have it for however many spins. It's just that probability times itself that many times, which is the same thing as saying, take that probability, raise it to the power of the number of trials, which is exactly, what our binomial function kind of simplified down to. When we wanted all the trials to be successes, it really just simplifies down to the probability of success raised to whatever number of trials we've got, right? And that's because that law of independence, right, is really baked into that binomial function. In order to be a binomial variable, the events had to be independent. So once we get to the point where we want to see what's the probability all of them are successful, just simplifies down to take that probability of success, raise it to whatever power you've got, or number of trials, number of spins, whatever the example is, right? So all these things are kind of related to each other. Here it's a little bit more kind of easy to connect the dots. On Monday, we'll go over the Poisson distribution. It is very similar. We're going to use a lot of the same principles. We'll use this idea of the complement rule. We'll think about like the distribution, how probabilities, as we move further from that mean, the probabilities begin to decline. So a lot of the same sort of things will apply on Monday. So we should probably go through it relatively quick. We might have a little bit of time for start some exam review, and then Wednesday will be purely reviewing for the exam. I'll mention more about more details about the exam in both of those class periods next week as well. Okay. Any questions for me before we get out of here today? Yeah. Unemployment data. Oh, so I think what I mentioned the unemployment data. I had a data set that had like income on it. It's just the data set. There should be an Excel file, right? That's the data I want you to use. So if I reference it as unemployment data, it's because I had a bunch of data from an unemployment data set, but the one I think I specifically use is income and kids for the Excel example. And that just came from that data set. But I got rid of all the other variables so that you knew exactly what you should use. Yeah, so it should be, here, we'll double check on this. So make sure I'm not telling you something. Should be the same for all these. So we'll go to Excel 2. So this data set, I might have to download. I don't know if it's going to let me view this in my web browser here. Yeah, so you'll use, right, these income. So this is where I'm going to re-upload this because this one it said 3, and in the Word document everywhere it said 2. That was really the value I wanted you to use was 2, but like I said, you could work through it the exact same way with 3. You're going to use this family income variable and then this number of kids variable or children or kids. Those are the only 2 that you need. We'll use that count ifs to construct the frequencies, turn frequencies into probabilities by just dividing by the total number of observations. And then the rest of it's really like questions you could kind of do by hand. I mentioned that in class when we worked through the example that was very similar to this, where I was looking at what was the one we did in class? The union stuff. Yeah, thank you. The weekly earnings and the percent unionized. It's gonna be very similar to that example. Okay. Good question. Any other questions before we get out of here? All right, so don't forget the online quiz will be up in the next 10-15 minutes. Make sure you get on and get that done before we begin class on Monday.